All right, today's lecture is on how to do atomic mass problems. So again, we've reviewed when we have an atomic symbol like the element carbon, for example, the number above the symbol is called the atomic number, right? The number right below that is called the atomic mass. So in this lecture, we're going to do is we're going to determine how did scientists figure out the atomic mass of an element. All right. So far, we've been utilizing subatomic particles to figure out how many protons, electrons, and neutrons there are. But this number on the periodic table, what is it? Well, the atomic mass is the weighted average of all the naturally occurring isotopes of an element. When we analyze an element, for example, you can see over here this pile of carbon that I drew a picture of. In this pile of carbon, you'll notice that all the black dots are the isotopes of carbon-12. But not all the isotopes of carbon are exactly the same. Some of them are a little different. They weigh a little bit more. And that difference in weight is due to the number of neutrons. They all have, because they're all carbon, which subatomic particle has to be the same? Protons. They each contain 6 protons. That's what makes it carbon. So if the nucleus has got 6 protons in it, it's automatically an isotope of carbon. Carbon-12, again, the number that follows the hyphen is called the mass number. The mass number is both the number of protons and the number of neutrons. Well, 12 minus 6 gives me 6 neutrons. If it's carbon-13, it's got 7 neutrons, and carbon-14 has got 8 neutrons. So the difference between these isotopes is simply the number of neutrons changes. Now, if we look at a sample of carbon, no matter where we get it from, the percentage or ratio of these atoms is always the same. And that is given by a mass spectrometer. A mass spectrometer is a device that when I send the sample into the machine to analyze it, it determines that 98.8% of all of the isotopes of carbon in a sample of carbon is carbon-12. Carbon-13 is at 1.1%. and carbon-14 is at 0.0001%, just a trace amount of the atoms. But again, when we have a small pile of carbon, there are 10 to the 23rd, a billion upon a billion upon a billion atoms, even in potentially a speck of carbon. So a trace amount, we still get a fairly large amount once we look at magnitudes that are measurable, okay? But we can see in this picture that almost all of the dots are black because they are carbon-12, and just a couple C13 and occasionally a red carbon-14 isotope is in that sample. Well, from this information, we can then figure out the atomic mass of an element. And really, it's a 3-step process. But because carbon-12 is so much, because carbon is so much carbon-12, the atomic mass, because it is a weighted average, we know that the atomic mass of carbon is going to be really close to 12, a little bit larger than 12 because there's a few isotopes a little bit more massive than 12. But we know the atomic mass of carbon is going to be right around 12 because so much of it is that element. The atomic mass of an element always lies closest to the isotope that it has the most of. Okay? All right, so the first step is to convert the percentages of each of the isotopes into relative abundance. Instead of having this be a number that adds up to 100, we want it to add up only to 1. So what we'll do for all of these is the first thing you should do is write down the percentages of all the isotopes. And we are going to convert these into or out of the percentage mode. To do that, we divide by 100. Or we move the decimal 2 to the left. Oops, my bad there. So the first one will be 0.989. The next one will be 0.011. The last one will be 0.000001. Okay, I think that's enough. 1, 2, 3, 4, 5. Okay. Once we have the percent abundances out of percentage mode into decimal form, we'll then multiply each of these by the weight of the isotopes. Okay, pull out your calculator now and go ahead and do the math here. 0.989 times 12, 11.868, 0.011 times 13, get 0.143, 0.000001 times 14 gives me 0.000014. We add up these numbers now. And we get 12.011014. Now in the periodic table that I've given you, and for the problems in the homework, I want you to round to 2 decimal places always to match the periodic table, and we get the mass of 12.01, which is exactly what it is on the periodic table. So this is how we do an atomic mass problem. The units on atomic mass are called AMU, or atomic mass units, and this mass unit is defined as 1/12 of a carbon-12 atom. Okay, so if I take a carbon-12 atom, its mass is 6 protons, 6 neutrons, and 6 electrons. Even though the mass of electrons are very small, for the sake of an atomic mass unit, it's included into it. So if we add up all these particles and divide by 12, that equals an atomic mass unit. By definition then, carbon-12 is the only isotope that has a whole number. If you look up the mass of carbon-12, it is exactly 12 AMU. It's a whole number because that's what it's defined as. Okay? Any other element, when you look up their exact masses, is never a whole number. So carbon-13, while we're going to do it for estimation purposes, if you look up the exact mass of carbon-13, it's more so going to be likely to be like 12.989924. It's going to be a number very, very close to 13, but not exactly. And that's because this carbon-12 is the only element that has this ratio of 6, 6, and 6 for protons, neutrons, and electrons. So it's just a small measurement of mass. It's not grams because these things are so, so small. Applying this, if you turn the page then, okay, what I'd like you to do now in this problem that I've given you on this lecture is I'd like you to pause the lecture and I'd like you to go ahead, and this is the mass spectrogram for neodymium. I would like you to go ahead and figure out what its atomic mass is by following the same 3 steps as the previous problem. So go ahead, pause the lecture, and go ahead and try and do it now. All right, so 27.2.272. So for all these, I'm going to get them out of their percentage mode. Bear with me, I'm going to kind of go over that answer key because there's so many of them. So there's 7 isotopes here. Okay. All right, so I jumped ahead here just so I didn't have to waste so much time going through, but if you need to, always pause the lecture now and look at the numbers. But going ahead and multiplying all these numbers out then, so again, make sure we move the decimal point over 2 for all these to convert them into their relative abundances. Okay, and then multiplying by the mass of the isotopes, 42, 43, all the way again to number 150. And then simply then adding up all those numbers that we get an atomic mass of 144.47. Okay, which is very close to the one in the periodic table. It's a little bit off, and that's mainly due to some of the rounding of these numbers, rounding these values to only 1 decimal place. If you were to leave these to 3, 4, or 5 decimal places, the number would get much more precise and get much closer to what you see in the periodic table. Okay, so that's how you do an atomic mass problem. Convert the percentage into decimal form, multiply by the mass of the isotope, and simply add them up. The very last problem at the bottom here is a more difficult problem. And that one ends up being to go backwards to figure out the percent abundances. Well, in a typical problem, okay, copper 63 and 65. So typically we would multiply the relative abundance by the mass of the isotope, which is 63. And we would do the same thing for the other one. We take the relative abundance, which is the percent abundance out of decimal percentage form. Okay, move the decimal. Then we'd add them together. And this would give me the atomic mass. Well, I know that the element is copper, and on the periodic table, the mass is 63.55 on your periodic table. Okay? So now the question becomes, how do we work backwards to figure out the percent or relative abundances? Well, the first key concept is this. What should the relative abundances add up to? So if I don't know this abundance is X, and this abundance is Y, what should the relative abundances of all of the isotopes of an element add up to? Not 100. 100 would be the percent abundances. For relative abundances, 100 divided by 100 is 1. The relative abundances are multiplied, or I should say are added up to 1. So if I set the relative abundance of the first one to X, okay, it would be X times 63. The X would be the relative abundance of the lighter isotope, plus, if I were to make this Y, you can't solve an algebraic equation for two different variables. Instead, what I know is that the value of Y has to be equal, okay, to 1 minus X. Whatever X is, for example, if X is 0.20, Y has to be 0.80 because they have to add or summate to 1. So if I know the value of X, I know Y has to be 1 minus that number. So that's what I'm going to plug in here is 1 minus X times 65. So the relative abundance times one of the isotopes plus the relative abundance minus 1 to get the new abundance times the new isotope. And this is the technique that we are using, which you used in algebra class. Oftentimes what you did is you created two systems of equations. 63 times X plus 65 times Y equals 63.55, and X plus Y equals 1. We created two systems of equations, and now we can either solve this by either doing elimination or substitution. What I've done here literally is do substitution to solve these two equations. So the first equation is summating the atomic mass and then recognizing that the relative abundances add up to 1, and we're able to solve this equation. So here's how, always in science class, we apply what you learned in math to a true real-life problem, and that's the beauty of this. We're utilizing the math to be able to solve a scientific phenomenon problem. Okay, so now it's the matter of doing the algebra. 63 times X is 63X. Here we have to do the distributive property. 65 minus 65X equals 63.55. Okay, we're going to move the 65 over to group like terms. That'll get rid of the 65 on that side. So 63 minus 65X gives me negative 2X. 63.55 minus 65 gives me negative 1.45. Dividing both sides by negative 2, again, going through orders of operation. And I get a value of X being 7.725. Now this is the relative abundance. To get percent abundance, we just simply convert to a percentage. Multiply by 100, and we get 72.5%. So 72.5% of all the copper is copper 63. The other one has to then be 100 minus that. So 100 minus 72.5, because the percent abundances should add up to 100, gives me 27.5% of copper 65. So this is the technique of how to go backwards. Going forwards with atomic mass is pretty simple. Move the decimal point, multiply, and add. To do these problems, which you have a few of them on the homework now, is just utilizing this concept of the two isotopes summating to 1 and solving utilizing substitution. Okay? If you want to use elimination instead, that's perfectly fine, whichever technique you're more comfortable utilizing. Okay? When you're done, you can always then go back and check your answers. Go ahead and take these percentages times their isotopes and see if they end up giving the atomic mass of the element. If they do, you know you've done the problem correctly. Okay? Again, do the practice problems now and check over with the answer key. And if you have any questions, please contact me.